Hello everyone and welcome to this video. In this occasion we'll compare the results from handmade calculations and S-frame analysis for the structure shown here. As you can see, it's a truss structure. That means its members will work as axial load only members. It is also pinned at point E and has a roller support at point C. It has two spans of 6 meters each and 4.5 meters height. Lastly, there are 3-point loads for joints A, B, and C, being 50, 85, and 60 newtons each. For this exercise, we're considering a Young's modulus of 200 GPa and a cross-section area of 250 square millimeters. It is important to note that it established the handmade calculations will use the virtual work method. So using the method of joints, we can calculate the actual forces for each member, starting from joint A or the point load of 50 kilonewtons at the farthest joint from the supports in the left side. As you can see in the diagram, the loads for all the members were calculated and indicated with the respective sign, as this one indicates if the member is working at tension or compression, being positive for tension and negative for compression. From seeing this, we can interpret about how the structure will displace. I like to note in the right side a little triangle. This triangle gives us a short explanation about how to calculate the components for diagonal forces. As you can see, and having an alpha angle, the components can be calculated using trigonometric functions, being commonly sine for vertical component and cosine for horizontal component. Now, in this view, we have the results from the virtual work. For a little of context, as we want the displacement at joint A, a single unit load is applied in the same joint, not having any other load in the rest of the structure. Following the method of joints, we can obtain the loads for the rest of the members. A short comment for the vertical member at the right side is that this one doesn't have any load compared to the previous diagram, as in this part of the exercise there is no load applied at the roller support joint. Also, for this example, the virtual loads have the same signs as the real load. Lastly, from the handmade calculations, we have the integration of all the data obtained and the displacement. As you can see, the displacement delta A is obtained from gathering the data from each member, multiplying the real force times the virtual force times the length of the member, all divided by cross-section area times Young's modulus. Following the process, we have 181.67 millimeters as final result of the displacement at point A. And now let's compare this with the results we can obtain using S-FRAME. Now we have S-FRAME open. In this case, I have a little grid prepared for this just to help to illustrate how the geometry is being represented. First of all, we have to define some of our members, so we go to the member definition tool. Well, before of that, we're gonna change the member type to truss and go from here to here, 6 meter span, and here another 6 meter span. So we have joints A, B, and C defined. For the joints D and E, we're gonna go for the join tool, and here we define 6 and 4.5, and then we go in for 12 and 4.5, and we have now our joints, all of our joints defined for this example. Now we need to finish connecting all of this through the member definition tool. Now we have this finished. Now to finish our geometry, we go for the support tool, and here we have the options for the support. The displacement in the x-axis is not going to be available for this in the joint C, so we define it here, and now it's indicated with a roller support. And for the joint, we just need to toggle this option and define it. Even if this appears like a vertical support, it's still working in the x-axis. So once we have our general geometry defined, we can go to the section properties tool, and here we can define, let's say, section this and go for moment of inertia of 10 and shear area of 10. This really doesn't add so much properties for this exercise, so it's not really important how you define it. But the important part is for the gross area. It's 250 square millimeters. So we go for add and close, and now the section is defined for our members. Now we can check on the material properties, and okay, the Young's modulus, it's the same as we are using in our exercise, in our hand calculation, so we can proceed with the next part. And for the next part, we are going to define the loads for this truss, for this structure. So we go for the loads window, and here we need to define our load case. So we go for new load case. This window pops up, and for the load case descriptions, we are going for point loads. In this case, the self weight is not being considered for any of the members. So for the gravitational factors, we are going to let them like this in 0 and 0. So we just go for OK. Now we have our first load case and the only load case for this example, point loads defined. Now it's time for joint load, and the joint load tool lets you to define some of the parameters to make a correct definition of the loads. First of all, we can define in which joints it's going to be assigned. So we can activate it and see 1, 2, 3, 4, and 5. In the direction, in this case, all of the point loads are in the y-axis, so we're not going to change this, but they are for x force, y force, and z moment. The scale load, we don't need to scale any of our loads, so we're going to let it like this. And the important one for this case is going to be the magnitude. So for this one, we are going to define -50 for this, -85 this, and -60. Press OK for this. You can drag a box, or you can click directly in the joint to define the load. So we have everything needed for our analysis. Let's get into it and see how close the results are. To run our analysis, we have two options. We can go to the Run menu and click in Analysis, or we can go to this option with Analyze. Any of these options will lead you to this window. In this case, we don't have a combination. We just have one load case, but it's okay. It's not going to be an issue for this exercise. So we click OK. Save changes. We're going to save it as exercise and run the analysis. We don't have any issue, any problem, or any error. Now we have the graphical results window, and here we can go to deflection tool, and here you can see the deflection in this structure. To see the results, we have two options too. We can go directly to toggle this option and it shows the values. But if we want to check more in detail, we can right click and go for properties, and it shows the results for the translation in x-axis and y-axis. And as you can see, for the results in S-FRAME, we have a deflection of 181.85, while the results in our handmade calculations are 181.67. These results are pretty close, so we can trust our handmade calculations were correct. Now, an extra, you can go for axial force diagram tool. Here you can see the axial loads for all the members, and you can see these are indicated in negative or positive. This means some of them are in tension or in compression, just like the analysis following the method of joints we did before.